Once again, look at Na2S4O6. In this compound, 4 sulfur atoms are there. Here it is not a single sulfur oxidation state. Definitely, here like this, maybe it is of course positive number, positive oxidation state, negative oxidation state, or zero oxidation state, or fractional oxidation state. Whatever it is, the thing. It is the average oxidation state because here 4 sulfurs are there. That's why this is average oxidation state. So, and also just average oxidation state we may calculate. Other method is there based on its structure. So I will explain later. Right now, Br3O8. Look at in this compound oxygen state of bromine. 3Br plus 8 into minus 2 equal to 0. 3Br minus 16 equal to 0. Therefore, 3Br is equal to plus 16 and bromine oxygen state is plus 16 by 3. Here also totally 8 oxygen atoms and 3 bromine atoms are there. It is also average oxidation state of bromine. Br is equal to plus 16 by 3. So this is also we can practice with the help of structures. I will explain you after these examples. Look at C3O2. In C3O2 generally it is carbon suboxide. Look at in this case oxidation state of carbon. 3C plus 2 into minus 2 equal to 0. In carbon suboxide, 3 atoms of carbon, 2 atoms of oxygen. 3C minus 4 is equal to 0. Therefore, 3C is equal to plus 4 and C is equal to plus 4 by 3. Look at in all these 3 compounds are exhibiting fractional oxidation states. In this case, plus 2.5. In this case, bromine plus 16 by 3. And in this case, carbon plus 4 by 3. So this type of compounds exhibiting, of course, this type of compounds are average oxidation states. These are because here it is not a single carbon, single bromine. It is not single bromine. It is not a single sulfur. For this case, or for this type of compounds, we may practice with other models once come to the point. For example, for calculating this type of compounds, look at we have to follow a few tricks are there. Look at first trick. First case. Suppose identical atoms. Between the identical atoms, a single bond is there, double bond is there, or triple bond is there, whatever it is the type. Suppose a single bond A between the two similar atoms. These are similar atoms. Between the two atoms, the oxidation state of first atom and oxidation state of second atom is equal to 0. Because after breaking this bond, here oxidation state of A is 0 and also second element also same, that's why 0. Suppose A double bond A is there. In this case also we can break the bond. So each atom's oxidation state is also 0. Between the two atoms, the triple bond is there. Here also we can break the bonds and here also oxidation state of each element is also 0. Suppose different type of elements are there. Different type of elements means different elements like A bond B. Here in different type of elements possessing different electronegativity values. Here in the first one, in this example, just we have taken A single bond between A double bond, between A triple bond is there. All these are same type of atoms. Between the same type of atoms, so maybe single bond, double bond, or triple bond, whatever it is, the bond is there. But each element is exhibiting oxidation state 0. But in this case of different elements, so in different elements means they are also having different electronegativity values. See, in A and B, look at the A bond B, between A and B, a single bond is there. Here, B is more electronegative than A. In this case, if you split the bond, A is exhibiting positive oxidation state because this bond occupied by B, because B is more electronegative character. That's why B oxidation state is -1. Now A oxidation state is +1 because A is losing the electron in this bond. That's why B is exhibiting -1 oxidation state and A is exhibiting +1. Suppose between A and B, double bond is there. Here again, B is more electronegative character. That's why B can accepts the pair of electrons. In this case, B is having oxidation state -2. Of course, B is exhibiting -2 oxidation state and A is exhibiting +2 oxidation state because A is losing the bonds and B is gaining the bonds. Between A and B, triple bond is there. In this case, A is exhibiting +3 oxidation state and B is exhibiting -3 oxidation state. Here, the different type of elements means these two elements are having not same electronegativity values. So both are different electronegative values. In this case, identical atoms, maybe same atoms are there, that's why they have same electronegativity character, same electronegativity values. So in this case, different elements. So just we are taking B is more electronegative than A. That's why in this case we are getting positive and negative oxidation states. Look at here. One more trick. Trick 2. In trick 2, depending upon electronegativity values, that's why we have to practice electronegativity values. Hydrogen electronegativity value is 2.1. Lithium electronegativity value is 1. Beryllium, boron, carbon, nitrogen, oxygen, and chlorine. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. See, look at these elements. So we should practice the electronegativity values. Very easy trick is there for these elements. Generally, hydrogen electronegativity value is 2.1. We have to practice that. Lithium electronegativity value is 1. After lithium onwards, till chlorine, we should add 0.5. So 1 plus 0.5. Here it is beryllium electronegativity value. Add 0.5 to 1. So it is 1.5. Add 0.5 is 2 electronegativity for boron. Carbon electronegativity 2.5. Nitrogen electronegativity 3. Oxygen electronegativity 3.5. Fluorine electronegativity 4. From beryllium to fluorine, just we are adding oxidation. Just we are adding 0.5. Next, sodium electronegativity value is 0.9. From magnesium to phosphorus, you should add 0.3. Magnesium to phosphorus, you should add 0.3. So 0.9 plus 0.3 is 1.2. 1.2 plus 0.3, 1.5, 1.8. And phosphorus electronegativity value is 2.1. After that, add 0.4. Here add 0.4. Here add 0.5. So, electronegativity value of sulfur is 2.5 and chlorine is 3. Suppose different elements are there between the elements, single bond or double bond, whatever it is. By using electronegativity value, just we can compare this. Suppose carbon and phosphorus. These two elements are different electronegativity values. Suppose beryllium and aluminum. These two are same electronegativity values. Lithium and magnesium. These two are different electronegativity values. By using these electronegativity values, we may identify is the element exhibiting positive oxidation state or negative oxidation state. Look at by using these elements. Look at an example. Suppose H single bond H is there. So it is a H2 molecule. In H2 molecule between two hydrogen atoms, single bond is there. So H single bond H means first hydrogen electronegativity value is 2.1, second hydrogen electronegativity value is 2.1. So these two are same atoms. So identical atoms. So if you split the bond between the two hydrogens, there is no change in its oxidation state. First hydrogen is 0 and also second hydrogen oxidation state also 0 because both are similar atoms. Look at one more example. H2O. In H2O molecule, oxygen is bonded with two hydrogen atoms. Hydrogen and oxygen, these two are not identical atoms. They are not same atoms, different atoms. So between these two atoms, oxygen electronegativity value is 3.5, hydrogen electronegativity value is 2.1. So which is more electronegative? So more electronegativity character of the element can accept the fate. That's why in this case, oxygen accepts this bond. So it is having -1 oxygen. And here hydrogen is +1 oxygen. In this case, here also oxygen is accepting this pair. So here also -1. So -1 and -1, it is exhibiting -2 oxidation state. Oxygen is -2. Each hydrogen is +1. Right? And look at one more example. Hydrogen cyanide HCl. In HCl, H single bond, C triple bond, N. In this case, look at first hydrogen. Hydrogen and carbon, which is more electronegative? Carbon is more electronegative compared with hydrogen. That's why this bond is accepted by carbon. So here, carbon oxidation number is -1 and hydrogen is +1. Between carbon and nitrogen, nitrogen electronegativity value is 3, carbon electronegativity value is 2.5. That's why between these two bonds, nitrogen is occupied. These three bonds, that's why nitrogen is -3. And in this case, between nitrogen to carbon, carbon is losing the 3 bonds. That's why carbon is exhibiting +3. Carbon is positive +3 between carbon and nitrogen. Between hydrogen and carbon, hydrogen +1, carbon is -1. Now look at the difference in carbon. Hydrogen is +1 oxidation state. It is exhibiting +1 oxidation state. Carbon is exhibiting +3 and -2. I mean +3 and -1. Carbon is exhibiting +2 oxidation state and nitrogen is exhibiting -3 oxidation state. So in hydrogen cyanide compound, hydrogen exhibits +1, carbon exhibits +2, nitrogen exhibits -3 oxidation states. Look at now, based on these electronegativity values, we may compare the previous examples. Come to the previous examples. Like, suppose carbon suboxide is a C3O2. Look at in C3O2, actually the average oxidation state we have calculated. So the average oxidation state of carbon in C3O2 is +4/3 we got previously. Once look at this now. Look at the structure of C3O2. In case of structure of C3O2, C double bond, C double bond, C double bond O, and here also double bond. This is the structure of C3O2. In this case, between carbon and oxygen, oxygen and carbon, which is more electronegative? Oxygen and carbon, which is more electronegative? Yes, oxygen is more electronegative. That is 3.5. Carbon is 2.5. That's these two bonds are occupied by oxygen. That's why oxygen oxidation state is here -2. This carbon is losing 2 bonds. That's why this carbon is exhibiting +2. Between these two carbons, both are same atoms. So both are same atoms means oxygen state of these two, it is 0. And again, between these two carbons, oxygen state, between these two also 0. But this carbon is bonded with oxygen, this carbon also bonded with oxygen. That's why this bond is, these two bonds are occupied by this oxygen. That's why oxygen state is -2 and this carbon is exhibiting +2. Look at now, average oxidation state of carbon. Here how many carbons are there? 1, 2, 3 carbons. Out of 3 carbons, central carbon oxidation state is 0. Left side and right side carbons oxidation states, each one is +2. That's why +2 and plus 2 plus 4 by how many total atoms? 1, 2, 3. So this is average oxidation state of carbon in C3O2 compound is plus 4 by 3. But look at according to its structure, this carbon oxygen state is plus 2, middle carbon oxygen state is 0, and right side carbon oxygen state is also plus 2. Look at Br3O8. Look at in this compound. In chemical bonding chapter, we have practiced these type of structures. In Br3O8, look at that. Look at left side oxygen. Compare it to oxygen and bromine. Which is more electronegative? Oxygen is the second highest electronegativity element. That's why here these bonds are occupied by oxygen. So here also oxygen state is minus 2. Here also minus 2. Here also minus 2. So all the atoms are occupied by the oxygens. That's why here bromine oxygen state is here bromine oxygen state 1, 2, 3, 4, 5, 6. So plus 6 oxygen states. Between two bromine atoms, these two are identical. That's why this bond breaks. So next, second bromine to oxygen. Here oxygen state. These two oxygens are occupied by these bonds. So this bromine oxygen state is plus 4. And between two identical atoms, bond breaks. And these oxygens are occupied by oxygen. That's why this bromine oxygen state is plus 6. Right, in Br3O8. I mean, this is a tribromine octoxide. In tribromine octoxide, oxygen state of first bromine is plus 6, middle bromine is plus 4, and right side bromine is plus 6. And each oxygen exhibits minus 2 oxygen state. Look at how average oxygen state is plus 6, plus 4, and plus 6. Plus 16 by how many oxygen, how many bromines are sharing these? 1, 2, 3. So average oxygen state of bromine in Br3O8 is plus 16 by 3. According to structure, first bromine is plus 6, middle bromine is plus 4, and third bromine is plus 6. Look at one more example. In case of other compounds like Na2S4O6, also we can practice like this. And also peroxymonophosphoric acid, peroxydiphosphoric acid, peroxymonosulfuric acid, peroxydisulfuric acid. So all the oxy acids also we can get the oxidation numbers with the help of structures. And one more example, Fe3O4. Oxidation state of iron in Fe3O4. In this compound, 3 atoms of iron, 3 Fe plus 4 atoms of oxygen. Each oxygen state is minus 2 equal to 0. 3 Fe minus 12, 3 Fe minus 8 equal to 0. Therefore, 3 Fe equal to plus 8, and oxygen state of iron is plus 8 by 3. So it is a fractional number. If it is a fractional number or integer, whatever it is, this type of compounds, it is called average oxidation state of iron. And look at its structure. Actually, this iron oxide, it splits into FeO and also Fe2O3. See, in this case, Fe3O4 decomposed as FeO and Fe2O3. In this case, oxygen state of iron is plus 2, and in this case, oxygen state of iron is plus 3. So Fe3O4 converts into Fu and Fe2O3. Here, oxygen states of here iron is plus 2 and here plus 3. And not only like that, if you are taking look at in this example, Fe3O4, 3 irons. First iron is having double bond oxygens, and here also double bond with 2 oxygens also later. So in this structure, Oxygen is more electronegative than iron. Oxygen also more electronegative. That's why these two bonds. Here oxygen, here each oxygen is exhibiting -2 oxygen state. Here -2, -2. Iron oxygen state, between these two irons, identical atoms. So same atoms. That's why this bond should be cancelled. And now in this case, oxygen state of iron is +4. And here also between two iron atoms, they are same atoms. That's why bond breaks and no charge. And here also say again, more electronegative element is oxygen. So in this case, oxygen state of iron is also +4. Middle iron oxygen state is 0. Left side iron oxygen state +4 and right side iron oxygen state is also +4. Now average oxygen state is equal to +4 +4 +8 by how many irons are sharing these values? Totally 3 irons are there. So +8 by 3. According to structure, suppose from left to right, left side iron oxygen state is +4, left side iron oxygen state is +4, middle iron oxygen state is 0, and the right side iron oxygen state is +4. So oxidation states in different compounds in different ions. So we may calculate like this. So thank you.